This is Dan Schneider, and on this Dan Schneider video interview, I have four men who have alternative views of the origin of the universe. They will present their views, they will debate with each other, and that will be coming up in a moment. We'll be going in alphabetical order in terms of which man will give his idea of the universe first, and then we'll receive questions from the other, and also on how they will present their ideas. First up is Howard Bloom. I have interviewed Howard two other times before, 12 years ago on my Omniverska internet radio show, and then also once in my Dan Schneider written interview. Howard, if you could just briefly introduce yourself and give a few minutes on your idea or your model of the universe.
Okay, my name is Howard Bloom. That's the easy part. Now for the hard part. I'm the author of 6 books. One of those books, the second one, Global Brain, The Evolution of Mass Mind from the Big Bang to the 21st Century, was the subject of a seminar put together by the Office of the Secretary of Defense. And they included in that seminar people from the State Department, the Energy Department, DARPA, IBM, and MIT. Some of them were flown in from Boston and from California. I've been the founder of several groups. One of them is the Space Development Steering Committee, which includes Buzz Aldrin, the second man on the moon, Edgar Mitchell, the sixth man on the moon, people from NASA, the National Science Foundation, and the National Space Society. I'm on the board and the board of directors, actually the board of governors and the board of directors of the National Space Society. And I'm designing right now, I'm co-designing a multiplanetary mission at Caltech for the Keck Institute for Space Studies. The alternative theory of the universe has my alternative theory of the universe has a strange background story. The year was 1955. I was 12 years old. My mom had somehow managed to get me a meeting with the head of the graduate physics department at the University of Buffalo. I had been into microbiology and theoretical physics since I was 10 years old. It was probably going to be a 5-minute meeting because what does the head of a graduate physics department have to do with a 12-year-old? And it turned out to be a 1-hour meeting because we were discussing interpretations of the Doppler shift, and specifically the interpretations that led to the Big Bang Theory. Now, in reality, Fred Hoyle, the man who was responsible for steady-state theory, that very year was absolutely certain it was the year he was going to destroy Big Bang Theory, and we would never hear of Big Bang Theory again. A few years later, 1959, I was 16, and I was working in the world's largest cancer research facility, allegedly working on pioneering research on immunology, but that wasn't what interested me. What really interested me was something called the CPT problem, the charge parity time problem. And here's the problem, if matter and antimatter are created in equal amounts at the same time, why is there so much matter in this universe and so little antimatter? It took me 2.5 months to figure out a solution to that one. And the solution was a Bloom toroidal model. A torus is a donut. Now it's called the Big Bagel model of the universe, and it works like this. Imagine an infinitesimally tiny hole at the center of the bagel. You know, one of those irritating bagels that doesn't have a real hole? At the instant of the Big Bang, the matter universe, our universe, the one we're familiar with, comes popping out at the top. The antimatter universe, in an equal Big Bang, comes popping out of the bottom. The two universes move at very high speed. How can you tell? Because the shape of the bagel, the sides are steep coming out of the hole. And the curve represents energy. The curve represents motion. So they're moving at very high speed. And then they taper off in speed as they get up to this sort of Placid, to use Terry's or David's term, as they get up to the top and the bottom where things smooth out. And then guess what happens? Then they begin to accelerate toward each other again, drawn by a common language. And that common language is gravity. So they increase in speed as they go down the downside, the outer side of the bagel, until finally they meet at the bagel's edge and annihilate each other in a flash of energy that is, guess what? The next singularity, the next hole at the beginning of the Big Bang. So it's what I think was Terry of the universe. And that's basically it. So what were the predictions that it made in 1959? One, that coming out of the Big Bang, the speed at which the universe expanded would be extremely rapid. In 1982, when Alan Guth presented his theory of inflation, that's exactly what Guth was proposing. And then in 1998, 38 years after the generation of this theory, we discovered something utterly shocking, that after a certain point, the universe doesn't begin to slow down, it begins to speed up, it begins to accelerate. Now, since to accelerate you need energy, we guessed, we hypothesized, we imagined, we fantasized an energy source. We called it dark energy. Dark simply means in physics, I don't know, I don't understand. But the Big Bagel model gives you a clear explanation of why the universe would be accelerating, because the negative, the antimatter universe, and the universe, the normal universe, have run out of energy, begun to sense each other's gravity, and like a descending cannonball at the end of a parabolic arc, have begun to speed faster and faster toward each other. So those are two predictions the theory made. I threw the theory away, thinking that if I was 16 years old and the theory was so simple, I could comic book science, not real science. But then when the predictions started to come true, I had to take my own theory seriously again. So if you look up Big Bagel, Howard Bloom, and YouTube, you'll find an animation of the theory, and that animation has had about 795,000 hits, moving up toward 800,000 hits. Now, all of us, David, Terry, not Lynn, we all have a similar problem. Three of us are not part of the scientific establishment. We don't have the right credentials to present our theories. And each of us has gone to great length and spent many years developing a really admirable theory, an alternative theory. So our problem is that we're outsiders. Only Ling is an insider. He has an academic position. He publishes in peer-reviewed journals. My theory was published in the Journal of Space Philosophy, which is a peer-reviewed journal, but it's certainly not Nature or Science.
Okay.
That's the whole thing.
All right, thank you, Howard. Up next is David Noel. David, if you could introduce yourself and talk about your model of the universe.
Okay. Hello, everybody. My name is David Noel. I live in Perth, Western Australia, but I was born and brought up in Britain, and I have a science degree from Cambridge University. For pretty much all of my life, I've been interested in how the world works, not just the scientific side, but also how society works, how people interact to get the results we see around us. Over the years, I've got in the habit of analysing what's called the conventional wisdom, what we're generally told are the views of the experts on all sorts of topics. Now, I'm continually surprised to find out how many of these views, how much of the conventional wisdom we rely upon is wrong. Sometimes completely wrong, more often just skewed because one of the underlying assumptions that the views rely on is wrong. You'll find my thoughts on various topics up on my website, aoi.com.au. Mnemonic is always of interest, although that wasn't the origin of the site name. Here's a little advert for the site. Now, for a sample of some of the worst misconceptions current, look at the Occam's universe on AOI. This has stuff on the physical cosmos. It's intended for any interested people and isn't very technical or complex. Now, here today specifically, we're talking about origins of the universe, and my model is called the Placid universe model, and essentially it's extremely simple. It's what I call Occamized, which means that we've used Occam's razor, which is a principle which says if you're presented with various alternative possibilities, you should always take the simplest. It was invented by William of Ockham, who was a monk, an English monk in the 1300s, but it's got tremendous application over any position where you have to decide between different alternatives. And the Placid universe model is completely simple. It says is infinite in space and time, and so it has no creation time. There is no expansion. It's pretty much the same from 1 millennium to the next. And it rules out the Big Bang Theory because there's no reason for it. Now, there's a couple of major problems with the Big Bang, which I'll just go into here. It's really one of the major mistakes in science, and I'll point out two assertions which are just plain wrong. One of them is common sense, and the other is more science. Now, the common sense item is, according to the Big Bang Theory, the universe exploded out of pretty well nothing from a small point around 14 billion years ago, and it's been expanding ever since. Now, if this is really true, then if we look back at the universe as it was in the past, then it should be more tightly packed than it is now. And we can do this because the light we see in our telescopes from distant objects started off well back in the past. So we look at galaxies from about 7 billion years ago. The light which we see from them started off 7 billion years ago. The images we see, which they're of the universe at the time which the Big Bang is, I think, is half the age of the universe, are not showing any compression. If the Big Bang Theory was correct, these ancient galaxies, which should be packed together twice as tightly as they are now in the closer, much younger universe. Now, they aren't. Even out to 10 billion or more light years, which is about 3/4 of what the Big Bangers say is the age of the universe, the images you get, like the Hubble Deep Field images from the Hubble telescope, show a packing which is pretty much just like the closer galaxies, those that are closer to the time. So that's a common sense item which relates to how closely the galaxies are packed. Now, the root science item, there's a basic scientific law called the law of conservation of mass energy. And that states that the mass and energy in the universe can be converted to other forms, but can't be created or destroyed. Now, it's a basic part of physics. You can't create or destroy matter or energy. You can convert them into different forms, and you can convert them into each other, but you can't create from nothing. Now, no instance has ever been found in science where the law is not obeyed. It's one of the basics, and yet the big theory completely contravenes this fundamental law. It tells us that matter and energy have been created from nothing and are continuing to be created. So in a way, it's astonishing that some people who call themselves professional scientists can accept the law of conservation and still believe in the Big Bang. Now, there's many other reasons which show that the Big Bang Theory is wrong. One of the particular papers I've got on this, articles up, is this one here, RIP, Expanding the Universe.
Can you hold it up a little higher? That paper, did you have a, yeah, okay, go ahead.
RIP, Expanding the Universe. And that gives a more detailed and scientific evaluation. So that's pretty much the position as it stands.
Okay, thank you, David. Third up alphabetically is Ling Wang, and he has another alternative model. Ling?
Okay, then do I just give a 2 minute of
first just give right, on yourself, and then
I'll go ahead with my 20 minutes presentation.
You just tell people who you are, and then talk a bit about your idea your theory.
Okay, I have 20 minutes, right?
No, no.
No?
It's
What?
20 minutes for everyone to introduce their theory. So just please tell us who you are. Give a minute or two on your background, and then 5 or 6 minutes, whatever you need to just talk about your theory.
Like an outline.
Yeah.
5 or 6 minutes?
Yeah. Just as David and Howard did.
Just an outline.
I thought I have 20 minutes. Okay, whatever.
Okay.
I'm a professor in the physics department of University of Tennessee at Chattanooga. I published my DET theory in the year of 2005 in Physics Essays. It stands for Dispersive Extinction Theory. It's a different interpretation of the Hubble law.
Okay.
From that different interpretation, my theory will allow an infinite universe, no beginning, no ending, and it's stable. And there's no ad hoc hypothesis. And no problems, no fundamental paradoxes, such as the violation of conservation law of mass and energy, horizon problem, geocentric nature, and extreme instability, none of these. And there are new physics in my theory. DT theory predicts that the cosmic redshift not only depends on the distance of the heavenly body from the Earth, but also proportional to the square of the line width and inversely proportional to the cube of the wavelength. And these are the physics not known before the publication of my paper. I have a detailed presentation later after the introduction. Is that good?
Yes, we will have links to all 4 of your websites and things below the video. So are you resting on that? So that you're
you give me a chance to give my presentation, right?
Yes, you will. Everyone will have. There will be questions. You can give a little bit further explanation when it's your turn to be questioned by the other 3. So thank you, Ling Jun. The fourth person to present his theory is Terrence Witt. I had interviewed also, like Howard Bloom, for my written version of my interview series, and his theory is null physics. So Terry, if you could introduce yourself and your idea.
Okay, my name's Terrence Witt. By formal training, I'm an electrical computer engineer. I ran a biophysics and biomedical company for 15 years, which became the world leader in cardiac analysis. But originally, when I was in college, back in the day, I started out in physics, and that has always been my passion, my drive. And that was around 1970s, where string theory was starting to fester. The Big Bang had been rolling along for quite a while. And once I got in education, I noticed how ossified and fractured and political, even in the 1970s, that physics had become. And I really didn't want any part of it. So I went into computer engineering. And then once I had developed later in my life, I decided, well, let's see if we can fix some of these problems. And so I published Null Physics in 2007. And it's a unified field theory. It touches on everything as a unified field theory should do, but it has a real strong cosmology section. And in the cosmology section, again, like David and like Ling Jun, it deals with a quiescent universe, a non-expanding universe, a universe that is very, very stable in equilibrium. But what it also does is it quantifies and it shows the entire cosmic engine, if you will. It shows how that happens. Because if you're going to say the universe is quiescent, then you got some explaining to do. Because the bottom line is the Big Bang, even though it is ridiculous, it is a fable. It is wildly inconsistent with several observations, not falsifiable. One of the basic things about science something has to be falsifiable. The Big Bang is not. If something doesn't match the Big Bang, then we create something like relic neutrinos, or we create inflation, or we create dark energy so that it will fit the data. That is not science. So it is not falsifiable, and that's a huge problem. And it is not predictive. The Big Bang looks for things that might match. It does not predict galactic properties. It does not predict anything. In fact, the original radiation field, when they're saying, oh, we found the microwaves, that's the leftover, that's the remnant from the Big Bang. Well, they couldn't predict that within 10 degrees. Now, many years later, we know it's 2.7 degrees, and so everybody's tweaked everything. It's like, okay, everything matches now. That's not science. Okay, no, cosmology is science. I take the quiescent universe, and I explain there are three big problems that you're going to deal with. If you're going to say the universe doesn't expand, if you're going to say the universe doesn't change, then you've got the redshift to deal with. Okay, and it is not a scattering phenomenon. It's a very specific. It looks exactly like a Doppler shift, but it is not. The other thing you need to explain is you look out into space, and everything you see is around 15 billion years old. It's not 10 billion, it's not 25, it's around 15 billion years old. So if the universe has been around forever, why does everything look like it's the same age, or right around that? Okay, and the third thing is the microwaves. That's a huge thing to explain, because in all cosmology, one thing that's typical is the accuracy of the measurements are horrible. The Hubble constant, it could be plus or minus 50%. The average density of the universe, plus or minus 100%. Those cosmic microwaves, we know those to several decimal places. That is the most accurate piece of cosmic evidence that we've got, okay? And the problem is, if you look at a star, or you look at a galaxy, those things are pumping out huge amounts of ultraviolet radiation, huge amounts. If you look at our sun, it puts out 2 or 3 parts per million microwaves, okay? So we've got this whole universe blazing away in ultraviolet, but yet when you look at the kind of radiation we have coming from deep space, the microwave radiation is 20 times the density of this integrated starlight. Basically, that's the term for, all the light that's leaving all the galaxies. We call it the integrated starlight. So now we're saying, okay, well, we've got contemporary objects, the galaxies that don't produce microwaves, but yet we've got all these huge density of microwaves in deep space. So we've got some explaining to do. It's like, well, where did all this microwave energy come from? And of course, the Big Bang says, well, it came from back in the day. And it did not. No, so if you're going to say quiescent universe, you've got some 3 very large things you have to deal with. And that's what Noel cosmology does. And in one paradigm, it not only deals with the redshift, the microwaves, the apparent universal age, but it quantifies the process. It actually looks, because, again, the universe isn't changing. We've got a lot of stars out there burning a hell of a lot of hydrogen, and they're making a hell of a lot of helium and heavier elements. If the universe has been here forever, we're going to have a lot of helium and heavier elements. There has to be a stability, and so there has to be processes in place in the universe to undo that nucleosynthesis. And the bigger trick is, okay, we've got all this radiation going into space. Now, back in the day, there was something called Olber's paradox. That was where they said, well, if the universe was infinite, and again, this is something you have to deal with if you've got an infinite quiescent universe. If the universe is infinite, then if I shoot a vector, a line out, any direction, sooner or later it's going to run into the surface of a star, because you've got an unbounded space. So the original Olber's paradox was saying, well, why is the sky black instead of white? Because if the universe is infinite, there'll be nothing but stars out there. Well, then they said, well, yeah, you've got scattering, and you've got a mean path before light would strike that surface, and so you've got diffusion, and you've got all these effects. But the other issue is, okay, so forget all that. You've still got stars pumping energy into the universe. If the universe is not expanding, all this energy just keeps pumping into the universe, the universe will die heat death. And so these are all issues that the Big Bang has tried to address. It asks, as an expansion, okay, we get cool. Now, I'm not saying the Big Bang is right. The Big Bang is as wrong as lug nuts on a birthday cake, okay? It is completely wrong. It is flat Earth wrong, okay? But what I am saying is there's some serious challenges when it comes to measurements that cosmology has to deal with. And that's what I did in my book. That's why there are equations in it. That's why there are graphs in it. And it takes about even an abbreviated presentation, which I thought, as Ling was saying, I thought we were going to get 20 or 30 minutes. That's why I brought up a PowerPoint that is like a 30-minute presentation. Usually it takes 2 hours to present all the details and the other bits in my theory. But it shows how the whole cosmic engine works. It shows where the energy, how when you create, you've got all this fusion. So you need fuel. The universe is a big engine. It needs all this hydrogen, right? And it creates compound nuclei and radiation. And somehow all that stuff, the compound nuclei and the radiation energy, get recombined to produce more hydrogen, so the cycle goes over and over again. And if you look at galaxies and you really understand what a galaxy is, it's all happening in galaxies. That's what a galaxy is. A galaxy is the universe's basically recycling engine. And so I can give you a very brief situation. So the three things we're talking about, the redshift, wow, it's a very unique thing, looks just like a Doppler shift. Well, everybody's so worried about the universe is flying apart, the universe is flying apart, it's expanding. What they don't get is it is energy loss. It is a huge energy loss because in 10 billion years, and light years, you have photons that lose half of their energy. So imagine the entire luminous output of our universe every 10 billion years, which is less than the lifespan of the sun. Every 10 billion years, it gets cut in half. Well, where's that energy go? That's a huge amount of energy. If you've got an equilibrium system, you've got a fire burning, and all this energy is going somewhere, and you need to account for that. Well, I'll tell you where it goes. The redshift energy goes by decay, by actual photonic decay, that gets dumped into the microwave background. That's why there's 20 times more microwave energy than integrated starlight. It's like, okay, well, then you have the equilibrium. Okay, so now you've got this huge microwave. In fact, if you look at the energy density in the microwave, and you look at how much, it's called luminosity density. That's how many watts per cubic meter stars overall produce into space. It's tiny. Space is huge. Space is empty. The luminosity density, which is measured, is about 10 to the negative 33 watts per cubic meter. So that's minuscule. It is so small that if you stripped away the cosmic microwaves, if you could just somehow blank out the entire cosmic microwaves, it would take our universe 940 billion years to replace that energy. So what that's telling you for the David and Ling that are proponents of the quiescent universe, that microwave energy field is nearly 1 trillion years old on average. That's how old it is, okay? And so now you've got this thing, so follow the energy. Okay, so we've got this energy going into the microwave field. And you can debate how the decay photons are emitted. I've got all the details in my book, but it's in there. Now you still got a problem. Where does it go from there? Well, the only place where it can go from there, it's filling up all of space. There's cosmic microwaves in every corner of the universe. It has to go back into the galactic systems. There's no other place for it to go. Okay, so we've got 1 trillion years worth of energy here. We're dumping more energy into it. As the stars burn throughout space, we keep dumping energy into this. Something has to get that energy back to complete this cosmic equilibrium. So that energy needs to come back into those galaxies so we can combine it with this really cool compound nuclei, carbon and nitrogen and all the good stuff, and burn it all the way back into hydrogen. And then we've got more hydrogen, make more stars, to make more term. It is an engine. Okay, so a lot of microwaves there. How do we get it back into the galaxies? Well, galaxies have a bright, shiny, cool spot, about 100 to 120,000 light years in diameter. The galactic disk, and I'm going to use, in fact, spiral galaxies are the archetypical perfect example of what I'm talking about, because you can look right at them and you'll know exactly, kind of like an aha moment. Okay, so we've got a spiral galaxy. It's about 120,000 light years in diameter. Outside of that spiral galaxy, and has been measured, is something called a dark halo. The dark halo of these galaxies is about 10 to 20 times larger than the actual galaxy. So if you look at the dark halo of the Milky Way, for instance, it's going to be on the order of 2 million light years in diameter. Huge dark halo. Now this is just dark, cold material. But what it is also is ionized at extremely low temperature, that would be around 3 degrees Kelvin, and it's got a huge amount of microwaves going through it. So what that is a basic galactic-sized microwave antenna. All these microwaves. So in the equilibrium system, what we have in our universe is you build up the microwaves to a density such that when they're passing through these galactic halos, it becomes a microwave antenna. And so that's the end of the electromagnetic energy. Now we've got electrical energy, because it's an antenna with microwaves passing through it. And so that electrical energy we see every day when we look at a Hubble telescope of a spiral galaxy, because those big bands that you see, those big beautiful bands in a spiral galaxy, is electrical current. And that electrical current is coming from the dark halo. And we know this because if you look at the cosmic microwaves, the only correlation they have to the visible universe. So if you were to take that big WMAP image and you overlay it onto the visible universe, there's no correlation at all. You've got the stippling about 18 to 20 microkelvin stippling through it. But what you will have is places where the two connect up. So now,
Terry, can you just wrap up in a minute or two?
Yeah, I am wrapping up.
Okay.
So those places where it connects up, the microwave radiation is cooler. It's a little less than 2.7, which means that's where it's getting drawn down to go back into the galaxies. The currents go all the way to the core, the galactic core, and that current plus is basically the energy returning to the galaxy, and now it needs to be combined with compound nuclei, and that's what happens in the core. And the only way to do that, because we've got a big galactic disk, is for the galaxy to be a vortex. So that's why galaxies look like a vortex, because they are. All of the galactic material falls into the core, it's combined with the electrical current, and it's burned back into hydrogen, and that's why you see jets of hydrogen coming out of the active galactic nuclei and a flow of hydrogen coming out of our core. And that is how the cosmic engine works. And our entire solar system is falling on average towards this core at 1.6 kilometers per second. We'll be there in about 4 billion years. It's 25,000 light years away. So that's prediction and falsifiability. If there's no galactic vortex, my theory is wrong. So my theory predicts, quantitatively falsifies. That's what science is supposed to be. That's
all right. All right. Thank you, Terry. So that wraps up this opening segment of the 4 models or theories of the universe. In our next 4 segments, each of the men will get a chance to just give a little brief recap and then accept questions in alphabetical order from the other 3 men, and we will do that in a moment. All right, continuing my alternative views of cosmology to the standard Big Bang model. In these next 4 segments, each of the men will get a chance to answer questions from the 3 other men. We will be going in alphabetical order. Howard Bloom will be first up. The questions will also be asked in alphabetical order. In this case, it will be Noel, Wang, and Whit. They will each ask 1 question at a time, and then if they have more, we will keep going around until each of them are exhausted, or we hit about the 20-minute mark. We don't have infinite room. So Howard Bloom, if you're comfortable with your opening presentation, that's fine, or if you just want to give a 20 or 30-second recap, that's also fine.
Well, let's give a recap, because Terry has a very involved theory of the shape of the universe, and mine is a little simpler. Remember, it's a big bagel theory, so the normal universe that we're accustomed to comes blasting out of the hole at the center of the bagel. The antimatter universe comes blasting out of the bottom. The two of them travel like a cannonball until they reach their furthest from each other, and then they start speeding into each other's arms and annihilate and become the next big bagel or the next big bang. So Terry or David said that the Big Bang model defies the first law of thermodynamics, the conservation of matter and energy. Well, the Big Bagel theory does not. It's a continual oscillating energy. It's like a giant photon in operation. A photon that travels, the universe is probably something that lives and dies over the course of something like 20 billion years. And Terry said that the Big Bang theory doesn't make any useful predictions. And my theory, the Big Bagel, made two useful predictions. One was inflation, and the other one was the dark energy, the acceleration of the universe away from itself past a certain point. Actually, the acceleration of the universe, in my theory, toward the antimatter universe drawn by gravity. So that's it. It's a very simple model. It doesn't involve any mathematics at all, although all shapes can be transformed into equations. That's what Descartes did with geometry once upon a time, translated geometry into equations.
All right, so first question up will be from David Noel. Howard will respond, and if David has a brief follow-up, that's okay. So David, do you have a question for Howard Bloom?
No.
Okay.
Well, I got it.
Sorry.
Coming out of, what was it, Oxford or Cambridge?
I don't accept Howard's view that his model doesn't go against the law of conservation of mass energy.
Oh, tell me why.
Oh yeah, I mean, if you want to answer Howard's question, you can. Why it doesn't violate, go ahead. But if you want to pass, I'll ask Ling Jun for a question.
Ask Ling Jun.
Okay, Ling Jun, do you have a question for Howard Bloom?
Yes. Let me ask Howard to explain something about your model. I downloaded your article which shows two pictures of your big bagel. Now, what are those? What are those axes of your big bagel? Say the axis passing through the center of your bagel. What is the axis stand for?
The axis was something the artist came up with in order to give you a quick visual explanation of the theory. In fact, those axes are not included in the Big Bagel at all. It's an Einsteinian space-time manifold. And it comes, as I said, steeply out of the bagel at the bagel's center, levels off at the bagel's humps, and then accelerates again or increases in its steepness again as it goes toward the outer rim of the bagel. But there are actually no longitudinal lines or latitudinal lines or anything of that sort. That was simply a convention that the artist used to get the idea across.
You have a correspondence of the supernova expansion picture to your big bagel, right? You got the inspiration from that. What's the correspondence?
That wasn't the inspiration. The inspiration, as I said, was the charge parity time problem, the CPT problem, which was haunting us all in theoretical physics in the late 1950s.
Is there any time axis in your big bagel?
Yes,
and all spatial axis. Huh?
There is a time axis, and
which one?
Well, now there's a difficulty there. The difficulty is that we all know what direction time goes in our universe. And the question is whether the time goes backwards. There are a lot of indications that that's the case in current theory in the universe below us, the universe on the underside of the bagel, the antimatter universe. So there, in all probability, according to the Big Bagel model, this universe is very finite. It certainly doesn't. Terry believes in a universe that has energy that's been around for 1 trillion years. This theory predicts an end to the universe in probably something like 5 billion years, a very finite amount of time, and then the emergence of a new universe. So the challenge for humans is the challenge that Stephen Hawking was debating when he was debating whether or not you could extract information from a black hole. If I sound what I was saying is that there was a big debate for a long time between Stephen Hawking and a number of other physicists about whether you can extract any information from a black hole. Presumably the universe will end in something that's the equivalent of a black hole. And the challenge for humanity in this universe is, in the 4 billion years or so that we've got left before the big, whatever you want to call it, crunch, is taking everything that we know and finding a way to thread it through a black hole so the next universe is wiser than our universe.
Okay.
Sounds like science fiction, but that's a major challenge.
All right. So the next question will be from Terry Witt. David, are you still there? Can you hear us?
Yes, I'm here.
Okay. What? Because you're rotating. If you could just turn off your video and turn it on again. But Terry Witt, since we have you and Howard, Terry, your first question to Howard.
Well, Howard and I are going to have some fun here. Okay, to start with,
Hold on. David should come back. So go ahead, Terry.
Okay, so I was referring to the violation of conservation of energy. I was referring to the normal Big Bang. In your theory, clearly you had a problem with the matter asymmetry and also the conservation of energy. So in your cyclic theory, yes, no, you're not. I agree, you're not violating energy. My question is, in your process, how do you recombine the electromagnetic energy? You've got matter and antimatter flying apart. So there's two issues. Well, here's why it doesn't really work very well. So you've got matter flying apart on the top of the four-dimensional manifold, antimatter flying, and then they're combining, they're attracting and annihilating on the edge, or the outer edge of your bagel. Well, the problem is you've got matter and antimatter scattered all across the surface of your bagel, and you've got electromagnetic energy scattered everywhere. So I want to know how you can get all that genie back in the bottle, number one. But part of that, I need to respond to your statement about predictability. Saying something's going faster or slower is not a prediction. 1.6 kilometers per second is a prediction. Okay, but for me, a prediction in science, you put a number on it. Because then when you measure it, then you say, hey, I hit the number. So that's what a prediction is for me. It's not, it's going to be rainy tomorrow, how rainy. It's a specific thing. So I'm just responding to your two things about predictability and conservation. So yeah, I agree with you. Yours does not violate conservation of energy, but I want to know how you get everything back, how you get the genie back in the bottle.
Well, let me make a statement. One of the stands out is because you have a shape of the universe. Einstein spent his whole life trying to determine the geometry of the universe, and you have a very clever geometry based on nothingness, actually. And the big picture counts, even if the big picture hasn't been mathematicized to make tiny little predictions. The fact is, if you make a big picture prediction and your big picture makes sense, a big picture can make an entirely new sense of the universe in which we live. So I'm a big picture person. Now, that's not to flatter myself. It means I have certain disadvantages. One of my disadvantages is I wrote a whole book on the history of math. It's called The God Problem, Why Godless Cosmos Creates. But I wrote it from the perspective of a person who is illiterate with equations, really can't handle them, and as a consequence has to understand the basic metaphors underlying a mathematical system like calculus. But understanding those metaphors, those big picture things, those shapes of things, but my collaborator in theoretical physics is at the College Institute of Applied Mathematics of the Russian Academy of Sciences. We published in Arxiv.org, and Arxiv.org is advanced mathematics and theoretical physics. You know that. And when I talked to him, and math is his thing, math is his life. And he has confessed that the only way he really understands math is by seeing the pictures. Richard Feynman understood math brilliantly, but he understood it through seeing the pictures. Big pictures count, and so do details. But without the big pictures, the details are meaningless. Without the details, the big picture is not finished. I'm just presenting a big picture.
Okay.
Well, no, I agree with that. But you took me to task when you said that you're predictive. So we have different interpretations of what predictive means. And I agree, the big picture is huge. My big picture is 0. Okay. And I go from that. But
no, your big picture is a geometry based on 0. It's something far more intensely intricate than just 0.
But my big problem is getting the genie back in the bottle, and that's what. How do we get all this energy scattered across a four-dimensional manifold? Because that the surface of the manifold is free space, and I agree you'd have those velocity gradients you're talking about with that geometry. But you need to get all that stuff back into the same density that it started with if you're going to have a cyclic system.
Well, that's for the annihilation of the matter universe and the antimatter universe on the edge. You get those things and they annihilate each other, but they create an enormous blast of energy. And
right, but
this universe.
Oh, I'm sorry. Go ahead.
No. All I was going to say is the first law of thermodynamics, the conservation of matter and energy, is respected in my theory, and I respect it. I take it seriously. Although, we've only seen a limited amount of this universe with very limited tools, and there could be big surprises to come. But the second law of thermodynamics, that all things tend toward entropy, that we're on our way to a heat death.
Okay, hold on, Howard. We're getting a hissing sound here. David, is that you?
Hello there.
David, okay.
Hello?
Who is that?
I don't know. I think it was coming from David. David, was that you hissing?
Yes, maybe I could comment on something that Terence and...
Okay. One moment. Let me Howard, just finish your comment.
Okay, I just wanted to say that the second law of thermodynamics is absolutely ridiculous. This universe does not tend toward disorder. This universe tends in the very opposite direction, toward order, complexity, flamboyance, ornateness. So once you've got the two universes annihilating each other in a blast of energy, what happens next? The universe starts organizing itself. The antimatter universe and the new matter universe start organizing themselves out of the universe, because the second law of thermodynamics should say all things tend to organize.
All right, so let me...
Dan, just one follow-up, please.
Okay.
My problem is they're not annihilating, Howard. They're spread all over your bagel. The only place where the annihilation is happening is a low-density, large volume on the edge of the bagel. That's what I'm saying. You've got these two fronts moving, and the annihilation is there, but look at the universe. Look at how widely matter is spread apart. If this universe were moving against another universe, to start with, it's such low density, the matter and the antimatter would just fly right through each other. They wouldn't even interact. That's
a very good point, Terry. It's a very, very good point. And I used the trick.
Hold on, Ling.
Okay. But I used the trick straight out of Cosmology. It was the trick of the Klein's bottle. Where the neck of the bottle comes up and then somehow magically goes through the surface of the bottle in order to become the bottom. So I use that in order to say that the outer edge becomes the center once again. Now, how that happens is beyond me, utterly beyond me. And the other thing that's beyond me is what happens with time on the underside of the bagel.
Okay, Terry, hold on. Let's go back to David. You can follow up.
Ling had a question.
Yeah, but David also had a comment, and I want to go alphabetically. David, you wanted?
Okay. Well, I could see what Terence's difficulty has been. Now, up on my website, there's answers to a lot more things than we've actually dealt with here. For instance, what the true origin of the cosmic microwave background radiation. But rather than opening that can of worms, in the papers there, you'll find an explanation of how the recycling of mass and energy occurs, and it's essentially at the supermassive black holes at the center of galaxies. They are absorbing mass and energy and putting out a great deal of mass and energy too in the jets emerge from those supermassive black holes are producing high energy photons and also protons and electrons, possibly starting off as antiprotons and proton pairs, but all that great mass of energy is coming out, and that's essentially the sort of that's what we perceive as the light from supernovas.
Okay, is there a particular question then for Howard, or was that just a comment? Hold on,
It's
Terry.
really to say that's the explanation of the recycling which Terence is seeking.
Okay.
Yeah, we've got questions for Howard now.
Yeah.
David.
Yeah. Let's. Do you have something directed for Howard specifically, David?
No.
Okay. Ling Jun, you had a follow up. Go ahead, Ling Jun.
I asked the Howard what are the three axes, and he couldn't respond. He was saying that the cosmology or physical theory is just a big picture, and there's no detail. Well, you don't have to give detail. At least you can tell us what those three axes are. If you
I think my difficulty is,
what a big bagel is.
I think
Right?
Well, hold on, let me
I
answer.
have a difficult time understanding what you mean by axes, because the axes are time, the
Well,
standard
like the
four-dimensional
bagel
axes.
we eat, like the bagel you buy in the store. You know
Well,
the three
but
axes, X, Y, Z axis. But what are the three axes of your bagel?
Well,
You know,
there's the three dimensions of
physics theory has to be quantitative. It's not enough just to have a picture, and you don't even know what the picture stands for.
Okay, so just.
I'm sorry, that's not accurate. You're asking me to put the big bagel in a specific set of scientific terminology that you find it easy to deal with. I'm sorry, we speak different languages, and we can both speak truth. So I'm telling you that for your axes, it's the standard three dimensions of space plus time. It's a standard Einsteinian
Well,
method.
there are four dimensions. Your bagel has only three dimensions there.
No, that's not true.
Specifically, what is the axis of the big bagel? Yeah,
I'm sorry, I do very poorly on algebra tests.
Ling Jun, hold on.
Again, Ling, because you're going to despise everything I say. So fine.
Yeah, Ling Jun, it looks like you're never going to connect. So let's move on, because I don't think Howard has an answer. So Terry, if you want to go.
Hey, Jim,
Yeah.
can I answer Ling's question? Would you
Briefly.
be okay with that, Howard?
Absolutely.
I think I know what he's asking.
Okay.
Should I attempt?
Go ahead.
Ling Jun, his axis is the curvature. The surface of the bagel is three-dimensional space. Okay? So it's the surface. So the bagel itself is four-dimensional, and the fourth axis is time.
There's no time in the big bagel, right?
No, there is time.
Axis, is that right, Howard? There's no universe expanding. Expanding.
It's the same.
Crucial axis.
So in the picture going back, matter and antimatter going back along the bagel and will meet each other. Apparently, there's a time axis there.
Well, there's two time axes, Lynn. It's the same as in our universe. If you look at the curvature around the massive object, that curvature is time.
Terry, let me just say, why am I asking the question? As a matter of fact, the axis of the bagel stands for time.
Yes.
Okay, so you agree. Then when you pass the top and going back to meet the matter and antimatter meet again, you are going back to the past of the history.
No.
That's what that's the essence of
I can't.
Howard. Let Howard, if he has a response, let him go, and then we'll have Terry ask if he has a follow-up question. Howard, do you have a final?
I don't have much of a response.
Okay.
Because time-space manifolds have been known for a long time. When Einstein was dealing with cosmological constant, he had a problem with it. He believed in the kind of static universe that all three of you believe in, and he couldn't make his equation for the cosmological constant hold still. The equation wanted to either become a curved universe in one direction or a curved universe in another direction. What's his name at Princeton said that that curvature basically is a matter of the fact that space tells time how to, or space tells matter how to move, and matter tells, or the curvature tells matter how to move, and matter tells space how to bend. I'm not quoting it as accurately as I'd like, But so this concept of curvature and its relationship to motion and time, and velocity, which is something that involves both motion, time, and distance. This is well known, Ling, and you are the master here, so you should know all of this.
Okay, so let's just end that right there. And Terry, do you have now a follow-up for Howard?
Yes, I'm going to stick with the getting the genie back in the bottle thing. So even if you change your topology so that you can get your rim of the bagel like a pine bottle back down to an infinitely small point. Okay, even if, so if we've got a bagel with a twist, we'll call it a strudel or whatever. The problem is you've still got matter and antimatter scattered over in, very, very large three-dimensional space, and it's also full of energy, and you're not going to have to take our universe and drop it into a black hole and crush it and cause another big bang. What I'm saying is, it's in any sort of geometry, big picture or small picture, this is not a cyclic process. You're going to have all this matter and antimatter scattered everywhere. You're going to have a bunch of energy, and if this wave comes through, and you get another annihilation, because you now have changed your topology so that you can get that density you need to make sure that matter and antimatter recombine or react, then you're just going to release more energy, but you're still going to have all the rest of the matter and antimatter scattered across free space, scattered across the entire surface of your bagel.
Well, I think that's a very valid criticism, and it's not something that I have thought out, so I can't at the moment answer except for the Klein bottle trick, which you've accurately characterized.
Okay, so let's leave it at that. So David didn't have any follow-up questions. Ling, do you have any other question besides anything on the axes?
Well, the next we may ask, where are we located on the big bagel right now?
Well, the acceleration Ling began because this has recently been discovered. If you accept the interpretation of the Doppler effect, what's been discovered since 1998, since the discovery of dark energy, is that the universe topped out at approximately the 7 billion year mark. And since the 7 billion year mark, it's been accelerating. So what does that tell you about the probable age the universe will reach? Somewhere not far from 14 billion years. We're not that far away from the crunch.
Okay, so
we're about to be meet the big crunch.
Well, not in our lifetimes, but much sooner than is thought in standard cosmology. Standard cosmology puts that date of either a big crunch or a big drift into no longer being able to communicate with each other at a trillion years from now. No, this says the universe is much more finite. The end is coming in a billion years.
Okay.
2 billion years.
So Terry, do you have a question other than any that you had previously asked? Something that's
No, I don't think so. I think my main concern, I was able to express it. Eventually, there has to be something you can get your hooks in to turn it into science.
okay.
And you said you got a graduate student in Russia or something that can do the math. But my other question is, if the universe is as young as what you're describing, I mean, you're changing the age of the universe substantially, right?
No, the universe is 13.7 billion or 13.8 billion years old. That's the standard. Those two numbers are the standard numbers.
Okay, so I'm sorry. So you said 7 billion years a couple times.
Well, 7 billion years is the hump of the bagel.
Yeah.
Okay,
That's where the bagel goes over the hump.
Okay.
Okay.
So let's end this then segment with Howard Bloom as the question. In our next segment, we'll take a break and we'll have David Noel try to get his visual back, and we'll have David Noel fielding questions from the other three men, and we'll do that in a moment. All right, I have David Noel back on video, and it is his turn to be grilled will do is if David wants to give a brief recap of his idea of the universe, we will then go, the question will go Howard Bloom, Ling Wang, and Terry Witt alphabetically. So David, do you have a brief recap?
Really just to say that the Placid universe model which I put forward is essentially says that everything is exactly the same on a long-term basis. All the changes we see are at a lower level, a closer level. The universe as a whole is unchanging and infinite.
All right, Howard Bloom, do you have a question for David?
Well, all of our different universe models depend on interpretations of the Doppler effect or the redshift, and whether the redshift is in fact the Doppler effect. So what is your interpretation of the redshift?
That the redshift is gravitational drag, as suggested by Fritz Zwicky. You can show that in fact the redshift can't be due to a Doppler effect as regards the distant galaxies and universe, because for if it's a Doppler effect, then the light from different parts of the same object which is receding must have the same redshift, and that isn't the case. If you look at the redshift spectra, you find that the amount of shift varies with the wavelength of the light. Now that can't happen with a Doppler redshift. I mean, there are Doppler shifts which occur with close galaxies, and you can have blue shifts as well as red shifts. But with the distant galaxies, you always find that the redshift is not fixed for different parts of the same spectrum, and it has to be if it's Doppler. So that really rules out it being a Doppler shift.
Why does that rule out a Doppler shift? David, why does that rule out being a Doppler shift?
David, he's asking why does that rule out a redshift?
No, why does it rule out a Doppler effect?
It doesn't rule out the redshift, it rules out the redshift being a Doppler.
Yeah, I'm sorry, I heard. Okay, so Ling Jun, do you have a question now for David Noel?
Yes. I also have a question about the explanation of the cosmic redshift. David is right that the redshift is not caused by the Doppler effect. But your explanation as due to the gravitational field may run into a geocentric theory. Because how can you explain the correlation between redshift and the distance of the heavenly body to the Earth?
Well, it's it's just an effect of gravity. The further the light travels, the more energy is extracted from it.
No, that's not right.
You say it's not.
Okay. Yeah, let him ask.
Zwicky pointed all this out at the beginning of the whole redshift business in the 1930s, and he did the math for it, and you'll find the references to that up on my sites.
Okay, so it looks like David has answered that. Let's move on. Terry Witt, do you have a question for David Noel?
Couple comments. You're absolutely right, David, on all counts. Quiescent, infinite, and in pretty much steady state. Really, the only difference I see with our theories is I've quantified it by using some of the astronomical and the cosmological evidence that I've been able to measure stuff, and by doing that, certain processes and certain other things that have appeared. One problem, so I really just generally agree, except, you have, like you said, you've got the development into a full science, into a full cosmology, but I guess I'm babbling, but do you have a reason other than the appearance of the universe? Do you have like an underlying first principle about why the universe is quiescent and not changing, or are you just going off basically its appearance?
Well, it's just a basic matter of logic, really. In a way, I'm saying that you don't need any theory. You just assume things are as they were, and you have to find a reason why that isn't so. Why the universe is expanding or not expanding. Now, the reasons put forward for expanding first the redshift thing, which I say you can, which I have shown is not due to Doppler effect. The other thing, of course, is the cosmic microwave background radiation, which as recently appears to be a normal black body radiation or second Boltzmann radiation from matter between the stars, which normally isn't visible, but it's just at the right temperature to produce the cosmic microwave background radiation. Okay. There's more to it than that, but you'll find that finely distributed matter between the stars is at about 2.7 degrees K, or 2.7 K, and that is the peak of the microwave background radiation. So it looks as though the cosmic microwave background radiation is just ordinary thermal radiation, which you'd expect from black body stuff at that temperature.
Okay, Howard Bloom, do you have another question for David?
I do have another question. Back in 1955, when I was meeting with the head of the graduate physics department at the University of Buffalo, Fred Hoyle, and I may have my year off by a year or two, but Fred Hoyle and George Gamow were both on the west coast of the United States. And Gamow kept calling Fred Hoyle and asking him to come down where he was, because he was doing consultancy for General Dynamics. He had just bought himself a great big white Cadillac that he didn't have the money to pay for. And if he didn't keep working every single hour, he wasn't going to get enough money to pay for it. And the two of them were arguing about the background radiation and its temperature. Both agreed that there should be a cosmic background radiation. And the guy who had the more accurate prediction was not George Gamow. George Gamow, of course, was the great champion of Big Bagel theory. I mean, Big Bang theory, sorry. The person who had the most accurate prediction was Fred Hoyle. Now, Fred Hoyle had a steady state theory of the universe in which you got these spots in the universe that he called something like creative zones, and they're just pouring out hydrogen all the time. So how does your theory differ from the steady state universe theory of the 1940s and 1950s?
Well, Fred Hoyle's theory, the steady state universe, does assume that the universe is expanding, but to counteract that, he postulated the spontaneous formation of hydrogen to fill up the gaps. Well, my view is that there's no expansion, so there's no need to have. That's
okay.
That
looks like
makes sense. Thanks.
Okay.
Slightly derogatory.
It looks like we lost Ling Jun here. Oh, he's coming back. Okay.
But the Placid universe is simpler than either of them, and it assumes that things are as they were and as they will be.
Okay, Ling Jun
Wang. How does the Placid universe? How does the Placid universe?
Hold on, Ling Jun, you just dropped off. I was just making sure. Okay, we got you back. Howard, just finish your statement, and then we'll go to Ling's question.
How does the Placid universe differ from the null universe that Terry has generated?
It has some similarities, yes. In fact, Terry has said that he mostly agrees with the views, or in fact, at least that our views are pretty close. His is just has got more sort of mathematical cladding, perhaps.
Okay, so let's move on. Ling Jun, do you have another question for David Noel?
Well, I agree with his notion of a placid universe and optimized universe. But the explanation of the cosmic redshift is not correct, because when you move through a gravitational field, when you move into the lower potential place, and then you come back to the place of higher potential, all your redshift and the bullshift will cancel out. So unless you have a global gravitational center, otherwise you cannot explain why the redshift is proportional to the distance.
Is there a question there?
Well,
okay,
let me just comment.
Go ahead, David.
What Ling Jun has said is the common assumption, but it is not correct. Light is affected by gravity, as is well accepted, with gravitational lensing and with gravitational redshift when light is emitted from an object and it loses energy, that it moves away.
Yeah.
Now,
let me just, before we go to Terry's question, just for the lay people out there, it seems to me that what you're saying, since light is known to bend, you are saying that that the ability to be bent around a large gravity field also sort of slowly leaches some of the power of light, so that over time and distance, going around many different objects, the light would basically lose. That the redshift is, I forget, there was an old term with redshifts that it's basically a weakening of the light every time it passes around a large gravitational field. Is that a lay person could understand something like that, David? Is that what your explanation is?
yes, but it's not really my explanation.
Yeah.
I mean,
you've incorporated. You didn't come up with it, but you've incorporated it.
Common was applied was tired light.
Tired light. Yeah, that was the
Yeah, but it was looked at fundamentally by a brilliant astronomer called Fritz Zwicky at the time that redshift was first being examined, and he showed mathematically the basic behind it, and he actually had the theory, the measurements, the magnitude effect looked at by astronomers, and it agreed with him that it was due to gravitational drag.
Okay.
Slowly the light is slowed down.
All right. So Terry.
Okay. The light is not, sorry, that's wrong. The light is not slowed down. It slowly uses a little bit of its energy.
Yeah. So it's leached
off.
Is
what's called the Zwicky constant, which is the distance at which light has lost half its energy, and that is somewhere around 7.8 billion years.
Okay. So Terry Witt, do you have another question?
Just a quick comment. Yeah, if you look at, in terms of this light, this tired light that the brilliant Fritz Zwicky predicted, if you look at the average curvature, we're talking about, if you like space like a rumpled blanket, if you look at the average curvature based on the amount of material that's in space, then you do get the magnitude of the redshift that we see. So what I'm trying to say is not only this a qualitative aspect, but it can actually be quantified, and that's what they did. But it wasn't quite as exciting as a big thing exploding billions of years ago. And so, and they also claimed that the redshift didn't cause the signal broadening, even though it does. So, yeah, and first, how to go on?
Okay, Howard Bloom, do you have another question for David?
No, I think that's pretty much it.
Okay, so it looks like you and Terry are done. Ling, do you have another question for David other than something about that? Okay, so it looks like then we finished the questioning for this round, and we will take a break. When we get back, Ling Jun Wang will then field questions from the other three men, and we'll do that in a moment. All right, I'm back, and in this segment, Ling Jun Wang will be the man to field questions from the others. He has requested to have a minute or two just to recap his theory. So Ling Jun, if you could go ahead.
Okay. My theory is a theory about the interpretation of Hubble law. The key question is to ban or not to ban. That is the question. And the key rests on the interpretation of Hubble law. We know Hubble law is a roughly linear relationship between the redshift and the distance of the heavenly body from the Earth. Now, the question is how to interpret this phenomenon. If we interpret it as due to the recessional motion of a heavenly body, so inevitably you run into the conclusion that the universe is expanded, and then you have Big Bang. However, if the real cause for the redshift is due to the interaction of the light coming from the heavenly body with the space medium, and then you cannot conclude that the universe is expanded. Infinite stable universe. DT theory is based on well understood physics of light material interaction. There's no ad hoc hypothesis. There's no postulation, and we can witness this in everyday life. The sky is blue. Why? Because the blue component is scattered more than the red component. The sun is redder in the morning and the evening. Why? Because it has a longer light path by glancing at the Earth. And we also know a well understood phenomenon in astrophysics that's called the star reddening. And this is a well understood phenomenon experimentally and theoretically. Even the galaxies will look red when it's farther away from us. So all this back up the interpretation of the redshift as due to the interaction, or it's caused in the process of propagation. Now, DT also predict new physics. That is, the cosmic redshift is not only dependent on the distance, but also proportional to square of the line width and inversely proportional to the cube of the wavelength. And these new physics are experimentally verifiable. It can be used to either vindicate or falsify DT versus BBT.
Okay.
Now, why do we need an alternative explanation or alternative interpretation of the cosmic redshift? Because the other interpretation would lead to a theory that has many fundamental issues, fundamental inconsistencies, and paradoxes. Even Hubble himself did not like that interpretation. But that the Doppler shift was the only mechanism he knew. If DT was published in 1920, he would adopt the DT theory instead of the Doppler shift. But the history took its own prerogative to allow the Big Bang theory to dominate astrophysics.
Okay, so with having said that, let's go alphabetically. Howard Bloom, do you have a question for Ling Jun?
Just it seems to me that Ling's interpretation of dispersive dispersion and extinction, in other words, scattering, he says in one of his papers, as the explanation for the redshift, makes a great deal of sense for at least part of the redshift, and seems totally consistent with what Terry believes. Terry believes in a form of that. Okay, I've got it wrong, so you have to explain the difference to me.
Okay.
And David believes in that all of this is caused by the gravitational redshift, by gravitational forces. One way or the other, what you call the space medium, dispersion by the space medium, is something that all three of you seem to agree about. But to a mind as naive as mine, they seem very similar to each other. But Terry sees a big difference.
Well, do you have a specific question for Ling Jun?
Yeah, I'm curious about what. I'm actually curious about what Terry sees as the difference between his interpretation and Ling's.
Okay, but this is you're asking how does Ling's dispersion of light and the redshift differ from Terry Witt's? I don't know if
Right,
he
exactly.
knows enough about Terry's to say that, but Ling, if you want to answer Howard about that.
Well, I guess Howard pointed out the difference between our interpretation of cosmic redshift correctly. My interpretation is based on well understood physics, the interaction of light and the material. The extinction includes both absorption and scattering. Now, Terry's explanation of the redshifts sounds very much like a tiled light theory, right? And as to David's explanation, I already asked questions. Unless you have a global or universal gravitational center, otherwise the explanation of gravitational redshift will not work, will not yield the linear relationship between redshift and the distance if you go into the quantitative analysis.
Oh, I can answer that. Is it my turn?
Oh, no, hold on. No, if David Noel is the next one with question. David, do you have a question for Ling Jun Wang?
Yes. Ling Jun, can I say that we're all pretty much in agreement that the redshift, cosmic redshift, is caused by some feature of space as light passes through it, which is proportional to the distance that the light has traveled. Is that fair enough? So
yes.
we're really only arguing as to the mechanism by which the light is reduced in wavelength. Are we all in agreement with that? We're just really arguing as to the cause.
Yeah, I think that's a fair assessment.
Well,
Right, with the exception of me, because I'm basically
the
Big Bang
distance
person.
actually, the distance is proportional to what we call the optic thickness, but it does not correlate to any gravitational center at all. As I said, if you go into quantitative analysis, you'll find a hard time to yield a linear correlation between redshift and the distance. If you insist that that's caused by gravitational acceleration, by gravitational field.
Okay, so basically, David, Terry, and Ling are in agreement that the Doppler shift is not the cause of red light. Howard disagrees.
It's incorrect. You're right.
So
I agree with that.
Okay, so Terry, do you now have a question for Ling Jun?
Oh, you bet I do. Okay, Ling Jun, your dispersion you're talking about is just basically scattering, right?
Scattering and absorption.
Scattering and absorption.
So extinction.
Okay, so that's the problem right here. The scattering and absorption cannot cause the redshift because scattering is just that. When you have scattering to conserve momentum, you're changing the direction of the photons. So you don't get photons that are pointed at Earth anymore. You get photons that are spread across space. Yeah, we can see images from 1 billion light years away where you can see galactic arms of the galaxy. Okay, so scattering, that's why scattering doesn't work. And then your prediction, you're saying that there's a frequency or a wavelength dependence on the system that you're predicting. Well, in fact, your prediction has already failed because that's how we measure redshift. If you look at the calcium lines or the oxygen lines, you have a pattern. It's like a fingerprint in the absorption spectrum. If the redshift was caused by scattering, what you'd see is a wavelength dependence in that, where now the pattern between the lines has changed, and we don't see that. So you've made a prediction for which data is already available that causes your theory to fail. And quickly, now, while you're true, the gravitational center that you're referring to, David, in David's information, he mentioned gravitational potential. Okay, that's true. Gravitational potential causes a redshift. What I'm talking about, and I think what David may have needs to read, or what he needs to rework is it's not gravitational potential. It does not require a gravitational. It is an additional effect. It is in addition to, yes, if you shine light from point A to point B, same potential, no redshift. Shine it up, you get a redshift. No, this is an additional gravitational light interaction that we're talking about. So my question to you is, how do you get an image from 1 billion light years away that is scattered? The light is no longer pointed at us. It has been scattered to conserve momentum.
Ling, do you have any?
Yeah.
Yeah, the question is, how do you account? How do you fix the angular problem? The conservation of momentum says scattering, a loss of energy or absorption scatters light. We see great images from great distances.
Okay.
So how do you account for that?
You finished?
Yes.
Yeah.
Okay. First, the light that we see are the surviving component of the light beam. Those scattered and absorbed are not seen. Does that answer your question? You said the line dependence, line width dependence and the wavelength dependence are proven wrong. That's not true. That has never been realized. In the past, when people measure redshift, they didn't realize that the redshift will be dependent on line width and wavelength. So they simply average out. Now, I dug out the data from the measurements. No such analysis on the redshift and line dependence and redshift and wavelength dependence ever been reported. And now there are people, I have some folks in Austria who are trying to come up with the experiment and test my theory. So that's what I meant. My theory is falsifiable. It's not something that you could never check experimentally.
No, I agree. What I'm saying is your theory is falsifiable. I'm saying the data that's already there falsifies it now. And I'm not saying line width. I'm saying line spacing. If you look at a calcium or an oxygen spectrum, there is a proportional spacing between different wavelengths, okay? And if you had the wavelength dependence of the scattering and you apply it to that, the proportions get messed up. You wouldn't even be able to recognize calcium anymore. Secondly, if the light that we see is the surviving light that's not scattered, then why is it redshifted?
Well, because the extinction is not constant. It's dispersive. As I said, the red component is extinguished more than the red component. And therefore, the peak of the Gaussian is shifted by the time it gets to the Earth. It's exactly the same phenomenon that we see. The farther the star, the redder it looks. The same phenomena we witness, and it's well understood. And this is same thing for the galaxy. The farther the galaxy is located, the more reddish it looks. Okay. And that's a solid proof that the blue component is extinguished more than the red component.
Okay, so let Terry, if you can follow up in a minute or let's have Howard. Do you have another question for Ling Jun?
No, I find this dialogue with Terry to be very valuable.
Okay, David, Noel, do you have another question for Ling Jun?
Only really to ask, aren't we all getting closer and closer together in our views, and really just the details are where we're differing?
You mean the three of you, Noel, Witt, and Wang? Howard is the outlier.
I'm saying we're really talking very much about the same conclusions. We're just arguing about the fringes, what color they are.
Yeah, basically, Ling, David is saying that he, Terry, and you are in a more general agreement than with Howard. So it's basically just details.
Correct. Well, we all believe that the universe is not expanding.
Yeah.
That I think, is that fair to say?
Well, yeah,
Yes.
that's fair to
But
say.
we are obliged to explain the cosmic redshift, and the explanation is different among three of us.
Okay.
Right.
So Terry, do
And
you have
what
a final question? Go ahead, Terry.
what I'm saying, Dan, the difference is important though, because we're coming up against the Big Bang, and things need to be quantified, things need to be able to predictable. I mean, the whole point of what I would hope the process is to eventually supplant a theory that's wrong. And in order to do that, we need to be right about the details too. And I agree we can argue about this, but what I don't agree is, if you're wrong, you're wrong. And yes, in fact, if you look in the color spectrum of distant galaxies, you don't see reddening because of dispersion. You actually see bluing, and that's the color evolution. That's one of the supporters or supports of the Big Bang. Is that, oh well, back in the day we've got younger and younger, bluer and bluer galaxies, but the point still remains that if this light came and is arriving and has lost energy, is lost by scattering, we're not going to see it. It's going to have a change in direction. And it's like looking through, if you look through a shower curtain or a fog and you see a light, yes, you're going to lose the whole glow around it. But photons you do see, when they get there, those are the ones that are not scattered. And so there's no way for those to have lost energy.
Okay, so
well, I do have one tiny question for Ling,
okay.
and that is in the dispersion model. What is extinction?
Extinction includes absorption and scattering.
Okay.
Two processes. So far, that's what we know.
Okay. So let me.
The extinction is not uniform over the whole spectrum. It's dependent on frequency. The extinction is greater for the blue light than for the red light. And if you look at the astronomical data, it's almost linear, roughly linear, over the spectrum that they observe.
And what does the term line width mean when you're referring to light?
Line width means, well, any spectrum line. Many people got a misunderstanding that a spectrum line is a single frequency. That's not right. Any real spectral line is a Gaussian curve. The frequency basically theoretically covers from 0 to infinity. Now, the Gaussian curve can be narrow, can be fat. So we define what we call the line width, which is basically 70% of the peak value for the electric field. And we define that as the line width.
Okay.
So it has nothing to do with the spectral lines that you see when you're analyzing the light from a given star?
Well, it depends on the source. For instance, quasars are known to have very, very large line width, very wide.
Which means they cover a very large part of the spectrum.
Yes, you're right.
And a smaller line width would cover a smaller part of the spectrum.
That could be partially explaining why the quasars tend to have a larger redshift.
And Terry disagrees.
Redshift, according to DET, is proportional to square of the line width.
Okay, so Terry disagrees with this.
Howard, the line width, think of this absorption. Now you've got a hot object, right? And you've got a specific energy that's getting absorbed. Well, a hot object does have a Gaussian distribution of material in there. So depending on the motion of that material that's emitting or absorbing the energy, the line is not going to be one exact energy. It's going to be thickened by the kinetic content of whatever is emitting or whatever is absorbing the energy. And this is well known. What I've been talking about is the distance between these lines, not the thickness of the lines. Now, the distance of the lines is characteristic of certain types of atoms. So that's why you get these nice mass spectrographs, and they hit things with a high energy pulse, and then you get this characteristic pattern that has the proportional distance between two states. And that's calcium, that's iron, that's whatever. And that's what we're looking at when we look at these things.
Okay, so it looks like David, Howard, and Terry have all asked their questions. Am I correct?
I think so, yes.
Okay.
Yeah.
All right. Let me just clarify something for any lay or young viewers, and let me just myself ask Ling a question, because since Ling's segment basically was devoted mostly to redshift and scattered light and that kind of thing, Terrence Witt seemed to have objected to the idea of scattered light because he said that redshift couldn't be accounted for that. I'm assuming this is something analogous to what he had mentioned earlier about Olber's paradox, which that if there are all these stars out of here, the scattered light, the redshift, the scattered light from one star might be scattered, but the star that's next to it and the star next to it, its light would be scattered too. So it would the scattered uh, the maintenance, the redshift would be the same, since one star's scattered light would intrude into another's. Again, I'm asking as a layman, does that have something to do with Olber's paradox? And is that your basic objection, Terry, to Ling's idea?
Was that a question for me?
Well, yeah, and then I'll direct it to him. Was that your?
Oh, okay, yeah. So the thing with the paradox is it's an energy flow. It doesn't have anything to do with scattering. It's just stars pumping energy into space and space getting hot.
Yeah, I know. But let's assume we had a universe with just one star, and as its light came 1 billion light years, you're saying that it would slowly diffuse out, and you don't think that's correct. But if you have a universe full of stars, each of their diffusions would sort of mesh into one another, and you wouldn't get the red shift. Is that what your contention is as why Ling's wrong?
No, my contention is you're shooting a. He's saying that the light is going through this material, and it's losing energy by interacting with material. What I'm saying is there's consequences to losing that energy through that mechanism.
Okay.
You can't, the thing is with the redshift, it's pristine. We get these pristine images of galaxies from very distant. And if it was actually running through material and losing its energy that way, it would be like what you're saying. You have photons coming from different stars, then all of a sudden they're scattered just so that they all show up at Earth in a beautiful image of a galaxy.
Okay. Ling Jun, do you have a comment then, a final comment to what Terry just said and my question?
So then apparently you didn't quite understand what Terry was asking, right?
Yeah.
Okay, so let me go back to Terry's question. Now, first I would correct the concept. Terry was saying that the scattering of photon, and that would reduce the energy of the single photon. But my theory is simply based on well-tested classical electrodynamics of Maxwell's theory. It's the light will reduce intensity. I do not need to invoke the concept of photon.
Okay.
So that's one thing I need to clarify. Secondly, the clear image you see is different from the accurate measurement of the redshift. For instance, you can see a very clear image of the moon, but it doesn't mean you can measure very accurately the redshift of light from the moon. These are completely different concepts.
Okay. I just wanted to clarify that because, as I said, this is on YouTube, so there will be lay viewers watching. So thank you very much, Ling. And in our final Q&A segment coming up next, Terry Witt will be the subject, and we'll do that in just a moment.